So again, you're only working on 1 and 3 here. You did not have to do number 2. Number 2 is a lot more complicated. If you did it, that's fine. And it's a tough problem. It's a pendulum. And I know Marie did it. She got it right. If you want to work on it yourselves, you can, guys. It's a very tough problem. We've got a pendulum at an angle of 5 degrees. Like that. That's the angle of 5 degrees with the weight acting down. And you have to think of the weight as a force and find the torque from that. Okay, it's a tough problem. It is. But you can definitely do it. Number 1. Find the magnitude of the torque produced by 30 Newton force or 3 Newton force applied to a door at a perpendicular distance of 0.25 meters. This kind of a problem. There's no angle given, right? And it says it's at a perpendicular. What's the angle really? 90. And you do sine of 90, but 90 is 1. Be careful, 1. So here.
Use your hand.
I never got that. You do that at all.
Okay, FRD, sorry, thank you, Karen. We used R yesterday, be consistent.
You would be sarcastic.
You can use your hand if you want to, or just memorize. Enough, let's do it. So, this is 3. It's in newtons, I can leave it. This is in meters, don't worry about it, just put a 0.25. Now I know sine of 90. Okay, what's a quarter of 3? 0.75. And my units are Newton hyphen meter. This is my torque again. Remember, your units are Newton hyphen meter, or Newton times meter.
What is the R again?
R is the lever arm, or the distance from the hinge, or the distance from the central axis that's rotating. So the hinge was the door we did yesterday. Okay? The distance from the hinge is R. The distance is 0.25. If the, put it away. If the torque required to loosen a nut on the wheel of a car has a magnitude of 40 Newton meters, and in this one they use Newton times meter. Okay? Same thing as Newton hyphen meter. Again, Newton times meter and Newton hyphen meter. It both means times. What minimum force must be exerted by a mechanic at the end of a 30 centimeter wrench to loosen it? So what are we trying to find now? F. We're solving for F. So we got, guys, why are you talking back there? It's not about this, so please stop. Torque equals FR sine theta. Now here, we're given the fact that we know that it's 40, so we can say that this is 40 here. We know the distance R. We're trying to find F. The hard part is this, and this is where you have to use logic. What is the angle going to be here?
90.
Why is it 90, Elizabeth?
It's perpendicular.
No,
it doesn't say.
It doesn't say it. Be careful. That's the hard part.
Hold on. Which one is it?
Number 3. Karen, your hand is up. Thank you. Any other hands?
Is it because you're going like this?
What did we say yesterday, guys? What's the easiest way to loosen something? When you push tangential, right? Remember we talked about it? If you're turning a wrench, you would push down. Then the center axis is here. You push down, then you push around, then you push up and around. It's always tangential. So the best way you can always open or loosen a nut or a bolt is by pushing at a 90-degree angle. So by saying the minimum force, it's indicating that make it easy on you, which is 90 degrees. Again, if you want to get the easiest way to do this, the easiest way for me to open this bottle, believe it or not, is to take it and twist at a 90-degree angle. So my fingers should really be tangential. This one should be tangential, so that there are 90-degree spots, and then I turn. If I turn where it's like this, it's not going to have as much of a required force here. So remember, when you're at 90 degrees, it's a lot easier. Okay? Like obviously, if you use your whole hand, it's easier to open, right? But I'm using 2 fingers. I want them to be at 90-degree angles, so tangent to the circle. So this is 90 because it says minimum. That's the reason why. How could you have 180? Think about it. Try it. So here, solve for tau.
You need to change.
Before, yes, you're right, we do have to. But let's solve here. We want to get F by itself.
Where you give tau? Yes, it is.
You're given tau, guys. Do I have to use the sine theta really in this problem?
No.
Because it's 90 and sine of 90 is 1, so you don't really need it. Keep that in mind. Again, it's really 90. So just divide by r on both sides. This is your equation for the force. Now, as Kenny said, look at the radius. Make sure you notice the lever arm or the radius is in centimeters. That's 0.3. So 13 1/3. And notice my units of force must always be newtons. And you can see, look, this is a Newton meter up here. This is a meter down here. A Newton meter and a meter, what happens to them? Cancel, cancel, you're left with newtons.
Yeah, how did you convert it?
Remember, 30 centimeters is 0.3 meters.
Mr. Hall, why did I get 133.33? That's what I got.
Because you used 0.03.
What'd you get as an answer?
40 divided by, I'm sorry. You know, what did I do, guys? What did I do?
You're the one who did it. You forgot to multiply.
What did I divide by, guys?
You divided by 3.
I divided by 3, but it's clearly 0.3, right?
Yeah.
So if we're dividing by smaller numbers to make my answer bigger,
149.
okay? So I'm going to have to move it over one spot like that,
You're bad.
okay?
Okay.
Thank you for the correction, Maria and Elizabeth, both. Okay, again, sorry, I apologize, move it over. But again, what I want you to notice is this too. Look at your meters, people. The meters cancel right away. You're left with newtons, that's your unit. Just check your dimensions to make sure they make sense. Okay, those are those two. Now, what I want to do today is this. I'm going to start something today that I did last year. That's not in normal level physics. It's really an AP physics topic. Okay? This is not like an easy topic, I'm telling you now. But if you do enough of these problems, it gets easier. And this weekend, I'm going to give you something to practice also. Okay? Yeah, it's going to be on the test also. Okay, but it's a good reason to do it. And I'm going to explain why we're doing it. There's a reason why we're doing it. It's not for no reason at all.
Oh, you know,
Why are you always having a radius?
now.
That's better.
Right? That's why we go back to what calculus
That's how
my answers are all wrong.
Physics, everybody uses degrees because it's realistic. You know what 30 degrees looks like. But most people don't know what pi over 6 is, you know? That's one. All right. So let's start with the problem. Here's the problem for today. And here's what I want to do. I'm going to take a vote to see what our answer is, and then we'll actually prove and see who was right. Okay? So before you answer, think. Imagine. You got a seesaw. Okay? Here's the seesaw. There's the fulcrum at the middle. Person A, let's say, Terrence, can I use your example? Wait, Terrence, how much do you weigh? You mind me asking? 160? Okay. So 160 for a mass of 160, 1 kilogram is 2.2 pounds. So let's say 70 kilograms approximately. So Terrence is sitting over here. His mass is 70 kilograms. Okay, let's say that he's sitting a distance of 5 meters from the fulcrum. That's one person. Who wants to be the other person? Kenny? Kenny, let's say, Kenny, how much would you say you weigh more or less than Terrence? Around the same? Less? Okay, so let's say, in this case, 60 kilograms. Now, we'll say that Kenny happens to be not 5 meters away, but we'll say 4 meters. So let me move him over a little bit, just so we're clear.
What are you trying to say, sir?
So, the question becomes, what effect does this have on the problem, right? The lever arm distance, the lever arm. And think back to when you were a kid. Forget math for a second. If you were on a seesaw, if you moved out to the furthest part, or if you moved into the closest part to the fulcrum, which one gave you more power in essence, or more torque? The further out, right? Just like we talked about yesterday. When I opened and closed the door, I didn't push next to the fulcrum. I pushed toward the end of the door to make it easier, right? If I push right along the axis, it's very difficult. Same thing here. So the further out you are, the more effect you have. So the problem here, and I should have done it backwards, really. If we want to really make this clear, guys, we should really have them switched. So go like this real quick. Put this as your 60, and put this as your 70. Okay? So what I want you to ask is this. What's going to happen with this problem? Is Terrence his side going to drop down, or is Kenny's side going to drop down based on this setup? So, just a simple vote. A vote first, then we'll talk about why. Who thinks Kenny's side will drop down?
Whoever's better.
Who thinks Terrence's side will drop down? Who's not really sure? Okay. So it looked like, for the most part, we got about 6 people voted over here. Nobody voted on this side.
I said I'm
Okay.
unsure.
Some people unsure, it's fine.
Won't they balance out?
That's what we're going to figure out. That's what we're trying to figure out right now. We don't know yet. We don't know mathematically. We do know this. You're right about thinking about balance, Julian. The heavier person, if that person is closer in and the lighter person is further out, there's a good chance they will balance. Yes. That's usually how it works. If you ever got on a seesaw with your sibling and that sibling was bigger than you, usually you went further out and they moved in to make it easier, right? Same thing. Okay? You ever been on a seesaw before?
In my neighborhood, the seesaw from
When I was a kid, my parents had a seesaw where you could actually move the seat. You could move in and out. I know. So,
you were lucky enough to have
in order to figure this out, here's what we need to do. Think back to yesterday, or Tuesday. On Tuesday, we talked about the possibility of having a negative or positive torque, depending on which way you're pulling. So in this problem, we want to start to think. We want to say this. On the left side, Terrence provides a mass of 70 kilograms, so his body weight is not just 70 kilograms, but weight, remember, is 70 times 9.81. So that's the force that Terrence is applying because of his weight. On this side, Kenny is applying a force down of a weight of 60 kilograms times 9.81. Again, your mass is 60, your mass is 70, but the force that you apply is your weight. So here, Terrence's weight is more than Kenny's, but he's closer. He's closer. What angle are they both acting at? They're both acting at a 90-degree angle. So right now, I don't have to worry about that. So on this side, if I want to figure out the torque provided by Terrence, and over here I want to find the torque provided by Kenny's body weight, I have to say, okay, what do I have going on here? So I've got a force acting down, and I know that it's force times the radius, or the arm, the lever arm, times the sine of theta. We said already that theta is 90 because they're both acting perpendicular down. So since theta is 90, I don't have to worry about that. So over here, the same thing. The force times the radius times sine theta, but I don't care about that. Now, remember, my force for each is different. My radius is different. So on the left side, my force is 70 times 9.81. Okay? What do we get? Approximately, let's say, 700. That's a good way to think about it. Here, think about this, guys. It's not really 700, but let's say it is. Because look, over here, don't you have 9.81 also?
Yeah.
So make them both 10. If you make them both 10 in your head, it's not going to have any effect on the problem, because you're doing it to both sides. Again, Christian, it's a very good point. Make this around 700 newtons. Make this around 600 newtons. Because really, if you make them both 10, then you're not affecting either problem, actually. Now, we notice that the radius here is 4, but the radius over here is... So, take a look at your numbers, guys. Which one's bigger in the end?
Terrence's.
Really?
2,800?
3,000? Be careful. This one is actually bigger. This one is actually bigger, and what we can do is this. Because he's further out, even though he weighs less, he happened to be further out by a bigger distance, so that compensates, and as Julian said, we're trying to find a balance. We're trying to see which one balances it out. Well, this one gives us 2,800 Newton meters. This one gives us 3,000 Newton meters. So Kenny has more of a torque. So which way is this actually going to go?
Right.
What does that mean, though?
He's gonna
Can't
go
say right.
down.
Okay, let's use our words correctly, people. We're talking about rotation. Julian.
Okay.
Clockwise.
Julian, come on, guys. I know it's right. I appreciate that, but please. I called on him, and he was about to answer.
Kenny's going to go down clockwise.
Kenny's going to go down, thus it would be clockwise. Very good. Again, if Kenny's side goes down, it means that the whole thing would go this way, right?
Yeah.
So in the end, it's clockwise. The reason it's clockwise is because Kenny's was clockwise, which is positive. Terrence pulled down on the left side, which caused it to go anti-clockwise, which is negative. So the net torque is just 200 Newton meters with a positive, which tells us clockwise Therefore, Kenny's side goes down. Again, what we're doing right now is we're balancing our torques. We're taking a look and we're saying, well, what is one torque providing and what is the other torque providing? See which one is bigger. See what happens in the end. So because of the fact that Kenny's torque was more than Terrence's, his side is going to go down. Again, it doesn't matter how big the person is. I mean, it matters, obviously, but really what matters is how big they are and how far from the fulcrum they are. How far from the central axis they're rotating. This is a very basic example to look at. The study you use this for is this. You look at beams and things like rods that are under different forces and to see what is going to happen in the end. Is it going to torque one way or the other? Is the torque going to be too much so that the actual object snaps? So that's what we're going to look at now. So we're going to look at an object where we have a beam with several forces at several angles at different locations and look and say, well, what's the net torque? What's the result of this? Okay? So we're taking a simple example of logic and applying it to more complicated.
So torque tells us how much force and how fast it's moving?
No.
Or just
Torque tells us the net movement direction. It will also indicate how fast if we start to use that, but we're not even going into velocity here. It just tells us which way is it going to move. Sorry.
Can you explain how it's different clockwise?
Positives clockwise, negatives anti-clockwise. Kenny, his body weight pulls down, which means if you follow my hand, watch, ready? He's going to get it to move down, and watch the motion. What does that become? Clockwise, right? So Kenny's became a positive 3,000. Terrence's weight is going to cause it to go down this way, and if I continue the motion, it makes it anti-clockwise, which is negative. No. Think about it separately. It's two separate entities. What would it do? Terrence is pulling down. Whether or not it happens or not, that's what he's doing. So his motion is acting down here, which causes it to turn this way. Even though it's not in the end, that's what we're thinking about. Think about it as if there was Terrence by himself. What would happen? It would go down, right? Going down means it would go counterclockwise or anti-clockwise. Thus, my number is negative. Kenny's weight by itself would cause it to go down over here, which would cause the motion to go clockwise like this. Thus, positive. So think about them as separate entities and numbers. And then at the end, combine them, see what the net is. Since the net at the end is positive, we know positive to be clockwise. Therefore, it's going to end up going like this, or Kenny's weight and fulcrum length will overcome the other one. Okay? Again, either way. Edgar.
does the whole progress and negative thing have to do with our frame of reference? Like if we were looking like 80 degrees.
If you were looking at it from the other room right there and you were looking this way,
Yeah.
then it would be the opposite, yeah. But again, remember, Kenny would be moving it this way. We call that clockwise, right? But if we're on the other side, then Kenny's still pointing down this way, which we would think of as anti-clockwise. So if you're looking in the Z direction from different spots, so he's saying, and we're looking at it this way, right? But imagine you're in Mr. Smith's room and you're looking at the seesaw from the other side. The signs would just switch, and you would end up with a negative here and a positive here. But it would still be motion where it would look like this, no matter what. But if I'm looking from my side right now, I see this as anti-clockwise. But looking from your side is looking like clockwise. So the frame of reference is very important. So another hand. Okay. So we got a beam. Let's start this one now.
Is this the thing that you're talking about we're going to learn?
Yep, this is where we're going to start now. So there's a beam.
So the last example,
What's the
wasn't it?
name of the cell?
Torque. We're still on torque. I'll give you guys the bells. The bells are off. A lot of stuff crazy. You see it down here. So we got, let's imagine a force acting down with a magnitude of 50 newtons at a fulcrum length of, let's say, 8 meters. That's our first one. Okay, we're still on torque, guys. We're still on torque today. The second one on this side, and I should put an angle here. The second one on this side acts at an angle down like this at 60 degrees, and its force is, say, 100 newtons at a fulcrum length of 6 meters. Okay? Again, we've got one object acting at a 60-degree angle at a shorter fulcrum length, another one acting now at a longer fulcrum length, but with less force. So the question becomes this, like, which way is it going to go, right? What does this one want to make it do? Spin which way? Show me with your hands. This way, right? Like that. So just like this, right? Again, this force over here. Think about it logically. Take your pen in your hand. Who spins their pen? Adolfo. Hold it up. When you spin your pen, Adolfo, when you spin it, show us how you do it. Okay, so now try and do it like slow motion. What are you doing? You're applying a little force to get it to rotate that way, right? It's the same thing here. If you have your pen in between your hand and you push on this side, it's going to start rotating this way. So when you push this way, this is fixed, right? It's a pin, it's fixed, it's not going to go anywhere. So it's going to cause it to rotate like this. But this force causes it to rotate like this. So we got to figure out, like a seesaw, which one acts more. In a minute we'll talk about, well, what if it's from the bottom? Same idea, still gets to push it. But we'll look at a simple example. So this is the same as the seesaw, but what have I done now? The degrees. The radii were different last time also. One was 5 and one was 4. They're still different, but now I'm at an angle. So this problem is the same. Okay, the problem is the same, but now it's at an angle. The point was the fulcrum from the seesaw. Think back. Remember there was a fulcrum at the bottom of the seesaw? That's what the point is. Absolutely. Look at the example. Sorry, you got to use logic. That is the point. Over here, I want to say what does this mean again? Net? What does net mean? Total, very good. We want to find the total torque. So we want to look at each torque individually. On the right side here, the 50 newtons, it's going to be the 50 newtons as a force times the distance, or the lever arm, times the sine of 90. Now, it's going to cause it to go this way. Take a look at my hand right now. It's going to cause it to go this way, which is positive, right? That's clockwise, so I leave it alone. The other one's going to cause it to go which way? Negative. So put a negative in front of the next one.
So that's why you subtracted?
Yes, and so I'm going to show subtraction. Subtracting 100 newtons times 6 meters times the sine of 60 degrees. Okay, that's all we're doing here. Again, it's not this. Again, this isn't tough, but I'm just telling you, it's not a normal thing that is covered in regular physics. It's more of an AP physics stuff. The only hard part becomes this, guys. What if we have like 5 forces? Then you're going to have 5 of these all lined up, and you got to be careful and go through each of them. And we'll talk about that, and we'll do a more complicated example. So here, multiply through. This is clearly 400 Newton meters. Again, I don't care about the sine of 90 because it's 1. Sine of 60 is root 3 over 2, or 0.866. This is going to be 86.6 times 6, 4 or 5. So my torque net will be negative or positive? Negative, again, because I'm subtracting a bigger number. So which way is this going to move? Counterclockwise. So I get negative 119.6 Newton meters, which really means 119.6 Newton meters counterclockwise. So if you write your answer, like this, or if you write your answer like this, that is fine. Okay, either way. But if I ask you in the problem, which way will it rotate, you have to answer with counterclockwise. Remember, if I say which way it will rotate, don't say negative. Negative doesn't tell me anything really, because some people call counterclockwise positive actually. Okay? It's always relative to what you choose in the beginning. We choose clockwise to be positive, we chose counterclockwise to be negative, so since I get a negative, it's counterclockwise. It's based on your choice. By the way, another way of thinking about this, remember how we count down to be negative? So we always said gravity was negative 9.81? Some physics teachers call down positive, believe it or not. I don't know why. I mean, I know why, and I understand it, because later on it drops off. But personally, I would call it negative, because we've always taught y-axis down is negative. Okay? So I'm considering clockwise to be positive, anti-clockwise to be negative.
So you can change it up.
It's up to you to choose, yeah. So if you go to college and your teacher calls clockwise negative and anti-clockwise positive, then you have to consider that. Good? All right. Let's go to a tougher one now.
What degree is that?
No, I would go back. I watched again. I was giving you the benefit of the doubt. I was judging like a kid, right? And so I watched it again.
I only have one question, is that the ones going up, those are negative?
That's what we gotta figure out. We're gonna talk about that now. Think about which way would cause it to turn. That's what you have to think about.
Oh, it's positive.
Okay, what's the problem? We see several things. First of all, first thing we're gonna notice is we don't have all of our lever arms. We've got the 5 and the 6, and then we got that 3 over there. Next, we've got 2 forces acting on the bottom. We got 1 up top. That's fine. Third, we have to look and say to ourselves, which way will the force cause it to turn? That's how you know if it's negative or positive. So over here, which way will this force cause it to turn?
Clockwise.
This way, right? Clockwise.
Positive.
So think of this with your torque in your mind. Think of this as a positive. Which way will this cause it to turn?
Negative, negative.
That way, right? So think of that as a negative, and this one?
Positive.
Positive. So please, write yourself notes for your torque. Okay, again, it's all about which way will it cause it to turn. That's how you know the sign. Now, I want to know what the net torque is on this problem. Okay, what is the net torque on
I have a question. Like, I know, you know where the 5 meters is? And, is that 5 meters for the whole stick or up to that point where it is?
Up to the point, so you look at the arrows. So,
No, but what I mean is that, like, there's no other force being applied before that?
no, so this, the end of the stick just goes off. There's
Okay.
nothing there.
Okay.
So we've got a 25 Newton force at a 45-degree angle at a distance of 5 meters. That's the first one. Then we've got the second one, a 50 Newton force at an angle of 60 degrees at a distance of 6 meters. What is this last distance, everybody? It's not going to be 3.
8.
What's it going to be? 9. The distance from the force to the pivot point, remember. So when you do this math, you got to use 9 as your length, not 3. That's the mistake there. 3 is the distance between these two, isn't it? But we always want the distance between the force and the lever itself, or the fulcrum rather, sorry, the fulcrum. So this distance is 6 plus 3, which is 9. 9. So I've got, I'm going to drop my units right now because they're all SI. That's the only reason I'm doing that. That times 5 times sine of 45. That's going to be a positive minus 50 times 6 times sine 60 plus 10 times 9 times sine 30. Okay, that's what your equation looks like. Again, we've got the first force acting at 25 over here. This one's acting 25 newtons at an angle of 45 at a distance of 5. That's this right here. This is the first force, F1. The second force happens to be pushing in the negative direction or the counterclockwise direction. Use logic. If you push up on this beam right now, it's going to go this way, which makes it negative, which gives us this right here. That's that part. Then the third force we know is pushing down on the right side, which causes it to go clockwise, which is this last part right here. So we have F1 gives you a torque for the first one. This is the torque for the second one. This is the torque for the third one. Sum those together, you get your net torque. Julian.
Negative 126.5.
And your units are Newton meters.
I got a negative 126.4.
Okay, just round, guys. If you round in different spots, it's different. I personally would write this all on my calculator in one line. Just literally type it the way you see it. It's going to do all the operations for you because look, multiplication always comes before subtraction. So if you put that all in one line, it'll do it the right way.
I hate doing everything.
What, you have something to eat? You have something to eat?
No, I don't like cornbread.
What does this mean again? Negative? Which way is it going to go? Counterclockwise. So my answer, the torque is going to go that way. So this beam will start to spin in that direction. Okay, we'll start to spin in that direction. I'll give you another minute to copy it down. We'll do the next problem.
Let us do it.
Say again?
You give us another one.
I'm going to give you another one, but before I do that, I want to do a different type of problem like this. Okay? And then I'll give you more examples to give you.
What was that?
I don't know either.
Right about now is when everything's going to get confused.
Okay? No, the next one's easy. The next one's very easy. You know what we're going to do now is, though, we're going to look at a beam coming out of a wall that's fixed. It can't rotate. We're going to see will it snap. That's what we're going to want to do. Okay? So, we got counterclockwise here because it's negative. That's why I drew the arrow this way. Because it's counterclockwise.
And then I can probably solve it. I have a question. If, you know how I do my ACL? Is it bad that I don't get surgery?
I'm not a doctor. I don't want to tell you this. I screwed up my shoulder when I was in like 11th grade and never got surgery. And it hurt for a long time. But like for the first time in years, it's getting better. Because I've been doing a lot of rehab on my own. Doing like workouts to help. I mean, it depends. It depends on how many you tore it too. Mine was a slight upper labrum tear.
I tore it.
It's not bad. Only a doctor can tell you that one. I can't. Not qualified.
He's not qualified.
How does the MRI machine work with that?
Oh, you put a minus again. That's the 10.
Is it bad to drink Gatorade like a regular juice? Or only, is it only good for sports?
Regular juice is better for you.
Does it have sodium?
They give you electrolytes.
Yeah, that's
You lose ions when you sweat, and it's giving you charged ions. That's all it is. All right, so let's say for this example, here's what we've got. We've got a beam coming out of a wall, so it's fixed into the wall. So imagine, if you will, like if you have not a flagpole, but like a
shelf thing?
Like that?
yes, like a shelf. Thank you. I couldn't even work with shelf.
Hey, look at me.
Oh yeah, actually like this right here. Sorry, like the smart board. So imagine if you will, that I was hanging off the smart board, which I'm not going to do here, and Karen got up there and hung up there, and Isaiah hung up over here. And the question is this: is it going to snap? Okay, is it going to snap? So let's say we know the max torque of, let's say this is, hypothetically speaking, let's say it's aluminum, okay? The max torque on the aluminum is
0.001.
the max torque that this material, and it's usually material properties that tell you this. So if you have like plastic versus metal, they're two different things obviously, right? Metal can withstand more. So here, let's say the max torque that this object can have is 500 Newton meters. And we know, again, somebody's hanging off here, okay, and the person's weight here happens to be 50 newtons. We'll say this distance is 2 meters here.
That's the worst place to stay. That's the worst place to grab from. Yeah.
Okay. Let's say at the same time, I asked Terrence to come up because he's tall, I can't reach it, and he can help by pushing back up. So somebody's hanging off the end, but he's pushing back up. Okay? So he's giving it support while someone's hanging on the end. So he's giving it support at an angle. because maybe can't reach straight up, he's pushing at an angle to keep it up. So he pushes at an angle, and we'll say that the angle he pushes at is 30 degrees, and he's able to push with a force of, in this case, let's say he can push with a force of 75 newtons. Okay? So he's holding this up while somebody else is hanging on this end of it. Okay? So he's holding this up while someone's hanging on the end of it. He's holding it up at a distance of only 0.5 meters. Okay, only 0.5 meters here. So what we want to think to ourselves here, hold on, I see your hand. What we want to think to ourselves is, we need to figure out the overall torque and see if it exceeds our limitation. Again, we need to figure out our overall torque and see if it exceeds our limitation. Let's say though, let's say here, because I'm looking at my numbers right now in my head, and it's not going to exceed automatically. Let's make this instead, let's make this a 50 instead of 500, just to be reasonable with our answer. Okay, so switch that to 50. I'm trying to check in my head.
I have, what is it considered, so you know how you're having like the person holding it up still supporting it, but what is it considered when like the other part where the person's hanging from like bends off?
What is it considered?
No, because like, I mean,
It's a force, right?
Yeah, I know, but I mean like,
It means if it doesn't
you
snap
know how
off,
we're
snaps
considering
right
the
there.
centripetal, like force all the way, like pretty much where it is in the wall, but then like, what is it considered to where like the guy is holding it up at 30 degrees from there to the end?
You're confused.
Still torque. I don't know. I don't know how to answer that. It's a torque applied at an angle, at a distance. It's another torque applied at an angle of 90 at a distance. Think about it. Maybe you can reword it for me to answer better, okay? Julian.
What's it called? So are the lines, not the lines on the side of the thingy?
Oh, these guys, sorry. This means you have a wall. Whenever you see lines like that, it means it's a wall. Just so you know, it's going to be all schematics so that way. If you want to draw the ground and a person standing, you really go like this. It just means some sort of a surface, okay? A fixed surface, meaning it's not going to move. It's like a building. Yes? So yes, that's what we have to think about. This one is pulling it this way, right? Positive. This one is pushing it back, negative. So we have to see what we get from those answers.
I would think it'd be the other way around.
If there were more than one, I'm just doing one for now.
So,
Yeah, but there could be more than one person.
so the person hanging off is positive?
You tell me.
Because I would feel like the person pushing it up is positive. And the
But you're thinking of up and down. Think about clockwise and anti-clockwise. Backwards. Again, guys, watch.
So they're both going this way.
Guys, come on. I'm waiting for you. Here, this is pulling down. So you're tempted to make it negative because you think down. But it causes the object to rotate this way, which is clockwise. So this will give you a positive torque. This causes the object to rotate this way, which is a negative because it's in counterclockwise. So when you're doing your torques, you need to apply the correct signs. Now, in this case, it really wouldn't matter because there's only two of them. But the minute we have three torques, then it does matter which is positive and which is negative. Because the answer you get will just be the opposite sign if you switch these up here. But if you had three torques, it would not work that way.
So, why is that one negative if it's pushing it this way?
This is pushing it this way, which means it go. Look, draw the arrow. Look, here's your arrow. Watch. Doesn't it go like that? Doesn't this arrow go like this? Use logic, guys. If you had a wrench and you were holding a wrench in your hand, and that was the wrench, and you push this way, it's going to go this way, right? Counterclockwise. If you pull down on the wrench, it's going to go clockwise. So a lot of it is logic here. A lot of it is logic. You know another way you can do it? I'm going to show you another way.
Is it an easier one?
Some people think it is. I don't personally use it, but watch. Start at the central axis where you're rotating. Put your hand, move your hand, or line up your hand as if you're aiming toward the force. Here's the force here. Put your hand like this. Then curl your hand in the direction of the force. Which way is that going to look?
Counterclockwise.
Then go this way. Put your hand that way. Curl your hand in the direction of the force. Clockwise. There's another way to do it. You don't have to do it that way. Use logic too. But again, put your hand here. This force is acting upward, so that's counterclockwise. Put your hand here. This force is acting downward. It's acting clockwise. It's another way to do it also.
Okay, so about the weight.
Yeah, sorry. Person's hanging straight down, 90 degrees. Okay.
I was
And that's the point, the focal point, 'cause you said.
Counterclockwise.
You said counterclockwise. That's
Did I?
allowed. Sorry. If that's the
So
focal
again,
point-
counterclockwise, clockwise here.
in between doesn't matter as long as you can take.
Whatever it's rotating about. Where could this rotate about? Only here, right? It's the only spot it's attached to. So that's the fulcrum. Okay? Let's do this. We got 75. There's going to be a negative in front of it. Times 0.5 times sine 30.
Oh, wait. That's,
Okay, which is also 0.5. Remember, this is negative in front of here, plus 50 times the full length, which is 2 meters, times the sine of 90.
I got it. It's 81.25
Positive or negative?
clockwise.
It's positive.
And as he said, Newton meters, not Newton watts. Okay. So here's your net torque. So what's going to happen to the object? It's going to snap. Again, take a look.
Oh, it's more.
It's all about snapping or not snapping, right? Remember, the net torque on this object is 81. It can only withstand 50. So this object would snap. This is how they study things. Here's a good application for you. You guys ever driving on the road and you look on the side, you see those billboards? That's exactly what this is. Turn your head, watch me. Go like this. And this is the billboard now coming out of the ground. And if there's wind on the billboard, the wind acts as a force. So I'll draw it for you. Here's the ground, here's the billboard, here's the sign. Okay, your car's driving here down the road. Here's your car, you're driving past the billboard. Now, if there's wind on the billboard, if there's a force of wind, there's a force of on the wind. If there's a force of wind on the billboard, it will cause a torque on that billboard. So if there's a force and the wind comes in and pushes with a force, it's going to cause it to torque that way. If the metal or whatever this is made out of can't withstand that torque, it snaps. That's what will happen. When I was in grad school, I spent a lot of time with a class called FEA, which is Finite Element Analysis, where you run a computer program that calculates all the stresses on the object. And we did this exact example. And what we did was this. We used a billboard and we modeled it as if it was a cantilever beam. This is called a cantilever beam. So we used a billboard and we said, let's think of a billboard as if wind is coming by. We then said, what is the wind speed? We converted the wind speed to a pressure. We converted that pressure over area into a force. And then we said, it's really like torque. And what we did was we wrote a program to solve all these things. So based on the material properties, based on the what's called the, it's not going to matter, but the modulus of elasticity, it's a value that is like density. Density is an inherent value. So the density of wood, or the density of metal, or the density of water, they're all numbers that are based on the property, right? The modulus is the idea of how much you can withstand also. So using the modulus, using the cross-sectional area, using the length of it, all these different things have effects on it. So one of the things that we did was we modeled a billboard as one of these beams. So these are really the exact same things. And that's what physics uses modeling. Remember how if you toss a basketball, we think of the basketball as a projectile or a point that's just moving through space? That was the simplest model we started the year with. We said the ball is really a point. The point is moving over a certain distance. Same thing here. This object on the right, this billboard, is the same as the example we just did. It's the exact same thing, but we're modeling it that way. Okay, so whenever you look at something that's very complex, make it simple. Dumb it down in a sense. Okay? Model it with an equation. All right. What I want you to do now on your own is practice one problem. You got about 5 minutes. You can do this one. You got maybe 3 or 4, yeah.
Why don't you give us a problem?
Pull out my homework. No. You look at it.
And what? Sure. Sure. As soon as I'm done.
Trees were meant to die for.
This is here. I have to add this to all of those, right?
Like cut on the tree.
My body's here. I have to add this to all of those. And then how come the other one was right here?
Uses that one. And that one uses, this one uses that one.
Now,
That one
before we
uses
get
this plus
started-
this, and then that one uses all of it.
Before we get started, I know you're copying, but look up for a quick second. Notice something. These angles here. I didn't ask you to talk, I said notice. This angle here is 30 degrees. That's 90, that's 90. See that angle of 30? What angle are we actually going to use?
60.
Why 60, Christian?
90 minus 30.
Because we're finding the angle here. Remember, the angle you're always using is the angle with respect to the lever arm. So if you're given an angle here, hint, if you're given an angle here, you want to use the other angle, or the complementary angle. So remember that this angle here is really 60. So when you use this one, you're going to use 60. 45, it doesn't matter, of course.
I mean, okay, no, I mean like if it's like 35, you use complementary.
Complementary, yep. Okay? Remember, you're always using the angle that's with the x-axis, the x-axis. It's like reference angles in pre-calc. It's the angle between the terminal side and the nearest x-axis. That's your reference angle. You're always using like a reference angle here. This would be like not the reference angle. This would be the angle between the terminal side and the y-axis.
Wait, hold up.
Okay, you're always using this angle here, even though it doesn't really extend.
All these are positive except that one?
No, you got to figure out what's positive and negative on your own. This causes it to go this way.
That one?
This causes it to go this way. This causes that way. This causes that way. It's 2 and 2. Finish this tonight. Write it down, please. This is your homework tonight. Please bring it in tomorrow. I have it done. I want to know what the torque net is on this problem. The overall torque net.
Oh, I don't know.
Okay, just for a heads up, tomorrow we're going to still do more stuff. I'm going to push back the review to Tuesday. The test is not going to be till Wednesday. Okay? Thursday, sorry, yes. So again, tomorrow we're going to do more torque, and we're going to do some stuff on black holes I want to talk about. By the way, I did proper impact.
Actually, no, I can't throw off my energy.
Oh, man.
Oh, well, you will.
I love this.
Oh, no!
Mr. Howe.
I don't
Mr. Howe. Are we using 30 or 60 as our
You're using what?
30 or 60? Are we combining them both?
You got to use the 60. Remember, you always got to use the angle that's with the x-axis. That's a 30-degree angle. That's a 90-degree angle. 90-degree angle. You got to use the 60, not the 30.
All right.
Okay? I think he already did just now. I'm going to put it online either way, guys.
When are we going to do like substitution with trig identities? I was looking at that yesterday and it kind of blew my mind a little.
There's a lot to do with that, yeah. The AP exam does not have as much of that, so we're not going to do too much. But we will get to it. I don't know when, though, to be honest. I got to get back to you on that. It's not, I don't know yet. We got to go. We're not even close to that yet. So we got to keep going. It's mainly used when you do like U substitution and stuff like that, which we haven't even learned yet. It's a method of integration. You have like a product of two numbers and stuff.
When you did something like U equal cosine of U.
substitution. We have to get there, we're not there yet.